So when people talk about genome editing being just like nature, because nature also makes DNA damage, what nature does not do is make that damage at predetermined locations, both intended and unintended, at will and at human scales on demand. It doesn't do that. So if there is an adverse effect that can come about because of its use, that adverse effect is also amplified.
Welcome back to another episode of the Force of Nature podcast, where we explore the ideas, innovations, and people shaping the future of food and farming. Here in New Zealand, the conversation around genetic engineering is heating up again. The government's proposed Gene Tech Bill could open the door for gene editing and other biotechnologies to be used more widely in our food and farming systems. For some, this represents a massive opportunity: faster breeding, new traits, and potential breakthroughs in production efficiency. For others, it raises serious questions about risks, regulation, and what it means for New Zealand's natural brand and export markets. To help us unpack the science, the implications, and the big picture, I'm joined by Dr. Jack Heinemann, a professor of genetics and molecular biology at the University of Canterbury, and one of the country's leading voices on biosafety, food integrity, and the social dimensions of biotechnology. In today's conversation, we explore what the Gene Tech Bill actually proposes, what farmers need to understand about these technologies, and how we can ensure that innovation and integrity go hand in hand. So without further ado, let's get into it. Jack, how are you today?
I'm very well today, thank you.
So from your perspective, what opportunities or risks should farmers be aware of when it comes to gene technologies like gene editing or GMOs?
The main thing about a technology, what makes something a technology, is that it's scalable. And that scalability comes from efficiencies. When that scalability is useful to a farmer, fantastic. But when, in the operation of that technology, it can also produce outcomes that could be adverse to the interests of a farmer, well, those can also scale with the same efficiencies. So as a farmer, what I would be concerned about with a gene technology is whether or not the regulations effectively constrain the scalability of producing bad things, or bad things along with the good things, as effectively as they release good things for the use by the farmer. So the issue with gene technology isn't whether you can sometimes produce something identical to what could reasonably be produced without the technology. That's not the issue. All technologies work the same way as nature. The atomic bomb is not something special to human beings. It still works by uranium atoms decaying as they do in nature. What makes it useful or harmful as a technology is that we can control where that happens, or at least influence where that happens, and the scale at which it happens, and the magnitude of that impact then is a human-controlled event, and that's what the technology is. So as a farmer, the issues will be whether any use of a gene technology has the potential to scale a harmful outcome, and that scaling effect could be effectively controlled by regulation.
That's a very, very poignant way to start this podcast. I guess if we bring it back to a lot of the terms that we've here thrown around when it comes to gene editing or GMOs, can you kind of highlight the key differences in, say, a plain language or something that a farmer can understand who isn't familiar with the terms? Because we hear genetic modification, gene editing, or CRISPR, probably some of the most common ones. So how would we understand those differences as a farmer?
Right. Most of that is a diversity of terminology intended to confuse and manipulate. Any use of gene technology, when it produces a living organism and the intention is to use that living organism, is making a genetically modified organism. The techniques to make a genetically modified organism range from the techniques that are routinely used to insert genes from other species into a genome to making higher rates of mutation, such as what occur in some reactions of genome editing, in order to accelerate trait development. All gene technologies have at their root that they are a direct way to intervene with the genome itself. Afterwards, you select what you want from it. So the main difference between those words, that word salad you started with, GMOs, genome editing, and CRISPR, is that what you're describing is an automobile. That's a genetically modified organism, and a type of automobile, say a Toyota. That's something you could create with genome editing. And then, even more finely, a type of color of paint, whether you're going to use CRISPR Cas to as the color for that automobile, or if you're going to use a ZFN or a Talon or any of a number of other types of tools or colors or variants of the techniques needed to create a genome edited organism. So these are just a continuum of description and detail of description. They're not fundamentally different classes of things. We have had the ability to both insert transgenes and to do what's being hyped as genome editing. We've been able to do these since the 1970s. This is not new to our science. It is true that the predominant released genetically modified organisms, the predominant form of genetically modified organism released into the environment, has been a transgenic, a series of transgenic plants. And that has, over the last 30 years, been the most familiar outcome of using gene technology. But that doesn't mean these other tools weren't available for the past 50 years, because they have been. What's different now is that the tools have become more refined and therefore more efficient and therefore more scalable for the same cost. So the tool CRISPR-Cas is a variant of genome editing tools we've had available for going on 50 years. But the tools we had then were like handheld screwdrivers compared to electric drills that have a screw attachment. So the efficiency and the changeability, you can put different screw heads into the, you don't have to have a different screwdriver for every screw head. All of those types of efficiency gains are being now available, become available through things like a CRISPR-Cas system. And the range of species that CRISPR-Cas works in is larger than some of the other more boutique tools that we've had available for the last 50 years. But they're not a new concept. They've always been considered by domestic and international regulatory authorities as tools that make genetically modified organisms. It is, in my view, a predatory attempt by members of the scientific community, some members of the scientific community, and by the industry to start to redefine genetically modified organisms as only those things intended to have genes from other species. And it's been a campaign. It's actually been a campaign from the industry and industry minded scientists since the early part of this century to redefine and nuance the kinds of outcomes of genetically modified organisms with the intention of creating confusion. And or if it's not with the intention, with the outcome being, the favorable outcome being, it creates confusion. And then they can turn around and say to you, oh, hey, don't worry about this because it's not what you thought a GMO was. But I'm sorry, technical experts for the last 50 years have always considered these things to be the outcome of a gene technology and the creation of a genetically modified organism. And it's because they have a common risk root. You can understand them in the framework of a risk assessment science. And that comes from the fact that whether you're introducing a transgene or introducing DNA damage, as you would with some kinds of genome editors only, you're accelerating the rate of mutation. Already in the mid 1970s, when the first types of transgenics became possible, as well as genome edited organisms, the scientists were talking about the fact that putting a transgene in, a gene from another species, was to effectively accelerate evolution by 10,000 years in one step, because you already have a fully evolved gene, take it from one species and put it into another. This was already being described in terms of mutation rate. At its most fundamental, genome editing does the same thing. It just does so at a place in the genome you want it to happen, and thus it's really efficient. It's more efficient than chemical and radiation mutagens, which also accelerate the mutation rate and have also always been considered gene technologies. The only difference historically between things like chemical and radiation mutagenesis, non DNA based ways to raise the mutation rate, is that because of other types of regulatory frameworks, it didn't require the outcomes of using chemical and radiation mutagenesis to be controlled by the same legislation because there was enough overlapping legislation to control the risk of a harm from those kinds of gene technologies. So the GMO regulations were made for the types of mutagenesis you can do with materials that are themselves not hazardous. Chemical and radiation mutagens are hazards and are already well governed under legislation for hazardous materials. But the use of DNA and proteins, which is the fundamental of a genome editor, to raise mutation rates, those things are not hazardous chemicals. So, new regulations, which we've come to know as GMO regulations, didn't regulate chemical and radiation gene technology, but did regulate these. Now, that historical distinction is again being used as a predatory move by the industry and some scientists to say we never considered those GMOs, but they also just increased the mutation rate. So why shouldn't we then deregulate these other kinds of gene technologies? Because either they don't know their history or they're being duplicitous in trying to confuse the listener about what it is that is fundamentally being addressed by regulation. And the fundamental thing that's being addressed by regulation is the scalability of an inadvertent harmful outcome.
That's awesome, extremely comprehensive, but it really gives us a good idea of the history of what we are dealing with. Because for some people, it might feel like it is a relatively new technology, but like you say, it's been around for quite some time now.
It's not a new technology, just new tools.
Awesome. So, for those listeners who aren't familiar with who you are, Jack, can you give us a bit of a background on who you are and what do you do?
Sure. Okay. So I'm a professor of molecular biology and genetics at the University of Canterbury. I've been here for over 30 years. And I've been a genetic engineer since my days as already as an undergraduate, but mainly as a graduate student in the late 1980s. And I grew up in the US. So I'm a lifelong genetic engineer. I'm a lifelong user, practitioner, scholar on the tools of genetic engineering. Since probably the early part of this century, so early in the 2000s, I founded a research center here at Canterbury that was dedicated to an interdisciplinary look at the impacts of gene technologies. And when I say interdisciplinary, I mean ethical, socioeconomic, different knowledge systems, pluralistic knowledge systems, as well as insights from people who are trained like me as practitioners of the science, of the technical science. And I have been involved with numerous countries and governments on issues of safety and regulation. And for the better part of this century, I've been an active member of the ad hoc technical expert group for the Convention on Biological Diversity, and in particular its sub-protocol, the Cartagena Protocol on Biosafety, where we look at emerging issues in biotechnology and try to provide guidance and guidelines for countries who are looking to control, who are looking to take the most advantage of safe, responsible biotechnologies through the control of those kinds of harmful effects that can come from the use of any technology.
That's awesome. What made you decide you wanted to go into this field all the way back then? Because it would have been somewhat still pretty new, as we've talked about already. But
All right.
what was the
Yeah,
catalyst
I
that
mean,
made you super interested in this?
Who knows? Look at you. You're asking me to look at my 18 and 19-year-old self, which is
Yeah.
it's not a pretty picture. I mean, I started university in 1980. So you're
Mm.
right. In 1980, as an undergraduate, a newly coming in undergraduate, the tools to manipulate genes directly weren't that old, right? They were tools that mainly developed very late 60s and through the 70s and had no commercial outlet by 1980, no commercial aspirations yet. Still entirely fundamentally an issue of basic science. Now, in 1980, I went to university thinking that I would be a business major, and in 1982, switched to science. And it had nothing to do with my premonition about genetic engineering, right? So I can't say that I made that decision based on this. But what I did note, I was at a large U.S. university, University of Wisconsin, which is also one of the fundamental homes of biotechnology. And in that, I had large undergraduate classes for biology, biochemistry majors. I had become a biochemistry major. And I remember my lecturers talking about 1982, 1983, saying that within 10 years we were going to have nitrogen fixing corn because of genetic engineering. We were going to solve all of the problems of inborn errors of metabolism, genetic diseases of genetic origin rather than just infectious diseases because of genetic engineering. We would be able to grow crops. Now I'm exaggerating a bit, but it gives you some of the sense of the hype on the moon because they would be impervious to drought or high concentrations of arsenic and salt. So, we already had the cell. We were being sold an imaginary, a technological imaginary in the early 1980s based on what genetic engineering was going to deliver. It's 2025. We don't have drought tolerant corn. We don't have corn that is fixing its own nitrogen. But what we do have is corn that will tolerate water stress many, many, many times better than corn did in the early 1980s. And why? Not because of genetic engineering, but because of good old crop breeding. This is what has delivered in the last 50 years. The major important agronomic traits in the staple crops that are also dominated in certain countries by GMOs, the traits that make them adapted to those ecosystems come from breeding. The traits that make them adapted to the use of high input chemical control, such as herbicides or insecticides, come from genetic engineering. We have learned how to concentrate the traits for things like drought tolerance, salt tolerance, heat tolerance, using molecular biological tools to identify those traits, but still using breeding to bring those traits together, to bring the appropriate gene variants together in hybrid elite lines. But we haven't done that with genetic engineering. And at the moment, there is nothing special about genome editing that tells me we'll make superior progress in doing so than we have made using crop breeding or breeding in general, conventional breeding in whatever organism we're talking about. But what we can do with genome editing is make a bunch of things that look flashy and have transient value. So we can change the color of apples, their flesh and their skin. We can make up stories about how this is the one thing that will save humanity because they're going to get a few more anthocyanins for a brief time from the 2 apples a week that they eat. So we'll make flashy things, colorful things. We'll make yeast that glow in the dark so you can find your beer even when the lights go out in the pub. But we won't make, or there's no evidence yet that we would make significantly more progress with genome editing than we have made with conventional processes. And that most of the resources for the good would go into those things that can be sold to bored rich people who are looking for some turnover in the varietal color palette at their supermarket. So, this is not to say that genome editing can't make a contribution. It certainly can make an economic contribution, and it can probably make a human good and an earth good contribution, but those aren't likely to fall out easily, and they're likely to be overcome by the kinds of distractions that make you more money than make you more good.
I think you've really highlighted something that I've become aware of is that the way in which we've plant breeding here in New Zealand, we've done some really significant and great gains in terms of yields and that with like a lot of our crops and our ryegrasses and all of that. Like we're almost world leading already. So what is like we're not going to gain this massive advantage that we already haven't already achieved through just regular plant breeding. So what do you say? Because we keep hearing that it's just a faster way to get our breeding to do natural plant breeding or animal breeding for the traits that we want. What do you say to that? Because that's always a classic comment that comes out around gene editing or GMOs, particularly with regards to crops.
I say it can be true. So if you know exactly what you need to change, and in all the places in the genome you need to make those changes to get the trait you want, that is what makes it a technology. You can
Mm-hmm.
create them faster, and that makes it scalable. But here's the side effect. These reactions, they're called precise, which is just a duplicitous term for efficient. These reactions are not digital. You can't tell a genome editor to only make damage at one discrete place in a genome. You can tell it to have a preference for that place. The differences in thinking, metaphorical thinking, is a lock and a key versus a magnet and a piece of iron. The more iron a material has, the stronger the magnet is attracted to that area, but it will be attracted along a continuum. It just settles first where the highest iron concentrations are. With a lock and key, the key doesn't fit into anything other than precisely the lock that it's intended to fit into. Now, with genome editors, they're more like magnets than they are like keys. So when you tell it to look for a particular gene, you're telling it to look for a sequence of nucleotides, A, G, C's, and T's. And at that point, attach and break the DNA molecule. But it's not a key in a lock, it's a magnet. So once it goes to its first preference and makes that break, it'll go then to its second preference, its third, its fourth, and it'll continue to act wherever it has or meets that minimum threshold. So the efficiency of the tools means that you can make your intended change in many different places in the same genome. You can make those faster than if you made no changes at all but hope to find them and concentrate them through breeding. But at the same time, you also make much more efficient all the changes at the places you didn't want changed. Those also scale, and you create them at unnatural frequencies. And this is the point. So when people talk about genome editing being just like nature, because nature also makes DNA damage, what nature does not do is make that damage at predetermined locations, both intended and unintended, at will and at human scales, on demand. It doesn't do that. So if there is an adverse effect that can come about because of its use, that adverse effect is also amplified. The way to use these gene technologies to maximize benefit is to use them under conditions where you have trained personnel in biological containment facilities that ensure that no unintended product is released into the environment. No changes in unintended organisms result in an organism unintentionally released into the environment. And until and only after you've confirmed that the use of the technology has produced precisely what you intended it to do, screened away anything else you didn't want it to do, tested and verified that it has the characteristics you're seeking, and then you release with social license into the environment. That is how it differs, and why it's so important that we don't take the kind of sloppy rhetoric that we've been hearing about, oh, it's just like nature but faster, because faster than nature is precisely how technology hurts us when it does hurt us.
That's awesome. So, if we bring it back to what is being currently proposed in the Gene Tech bill and we kind of just focus on the agricultural part, what do you think it would mean practically for New Zealand farmers based on everything we've already talked about around? I guess the biggest concern for me would be that scalability.
Yeah, so what this gene technology bill does, the only thing it does that makes it different from existing regulations is that it allows harm to scale. So farmers become more vulnerable to that scalability of harm. Let's just be frank about things. The gene technology bill creates no new enablements for New Zealand. You can already create any kind of genetically modified organism you want to create under existing legislation. The difference is that under existing legislation, you have to do it in containment, in biological containment, and you have to at least demonstrate to an interested regulator that you will not cause more harm in releasing the organism than benefit to New Zealand in releasing that organism. So the release stage is controlled by a regulator. The new bill does the same thing. For some GMOs, it does the same thing. You still require a regulator to look at it. But for some uses of gene technology, it does not require you to have a regulator look at it. They completely deregulate the use of some forms of gene technology, which means that anybody can use those gene technologies in any place. They can do it in their homes, they can do it outside schools, they can do it inside schools. If they're using those types of gene technologies, those tools, and their intention is not to create something that would cause harm, they can do it without telling anybody. So the amount of experimentation, the amount of frivolous, whimsical use, or even use by practitioners such as myself, but which is ill intentioned, is arrogant, fails to achieve that minimum standard of care that is currently required under the legislation, that would be okay. And that means for farmers that they have all sorts of new risk pathways for their primary product. As an example, I can go around now, if this bill passes, I can go around and I can tinker with yeast. Because if I'm using a certain tool, and if I'm using a certain species of yeast, Saccharomyces cerevisiae, it's okay. It's deregulated. Do whatever I want. And who knows? I might have all sorts of utopian ideas about what I can do with yeast. And I might try and fail to make a yeast of the type I want. But at the same time, I may create a trail of yeast that nobody wants, that are, for whatever reason, in whatever context, superior in fitness to some wild yeasts. If you're a winemaker, that might be a problem because all these little tinkered yeasts can maybe colonize a vineyard. They'll get into your wine. They'll get into your stock for fermentation, for beer. They may even get into your stocks for dairy products because, yeasts, they're everywhere. Now, they may not survive those processes, but their DNA will. And as detection tools also improve, there will be the possibility that either ours or a foreign government to which you're exporting your unintentionally GMO material to detects something that's out of the ordinary. Then there's a problem because most jurisdictions that we sell to have zero tolerance to unknown genetically modified material. So if they have a hint that there is a GMO in there, they don't have to prove there's a GMO there. You have to prove there's not a GMO there. And if they start to get signals from their routine testing of abnormalities in the genome sequences of contaminating DNA material, which is normal. You normally will have these other genomes in any product because there's always going to be microbes on anything we produce, and it's always going to be in our food. If they start to see these signals, though, they're going to question whether or not there is an attempt to use a GMO or there's a bioterrorism concern. And they're going to ask you, as the exporter, to prove that what's in there is either not a GMO or is an approved GMO. This is another way in which the industry is manipulating us. The industry turns around and says, and when I say the industry, I mean the biotechnology industry. They turn around and they say, look, there's tolerance for GMOs everywhere in the world. European regulations, Brazil, Japan, Asia, they all will say you can have up to roughly 1% contamination with genetically modified organism genetic material in a product that you're claiming is non-GMO. So it's not an issue. But what they're not telling you is those tolerances are only for approved GMOs. Those are for GMOs which that regulator can cite the safety data for. They're not for GMOs that Jack made in his garage because they became deregulated in New Zealand and he could tinker in his garage in New Zealand and it contaminated an export through some pathway that was alien to Jack, but nevertheless got there and has never been cited by a regulator and it's never been tested for safety. There's zero tolerance in those jurisdictions for unknown GMOs.
Yeah, that's very scary for an exporting nation. How easy is it for someone to actually do this in their garage, or say for a farmer to start tinkering with these things? Because I guess as Kiwis, we love to be number 8 wide and come up with new inventions. And if we've got the opportunity, there'll be some smart fella out there who actually has the capability to do this on their farm.
The ease of use varies with species, but what I could say is it's way easier to use these tools and create what you don't want than it generally is to use these tools and create what you do want. Another form of manipulation, and I hear this mainly from our plant biotechnology community. They'll talk about how these tools are still too difficult for someone to use in their garage. And getting that plant trait that you've been trying to get, it's just not simple. It takes months and months, if not years, of using these tools for even a skilled practitioner to achieve success. And yeah, that's true. If you want to use these tools to create what you intend to create, and also to intend to create something that would be of value, they can be difficult to use and it can be hard to be successful. But it's not hard to use the tools to create what you don't want. And that's the same thing with chemical and radiation mutagenesis. Just because it's hard to create the kind of plant you want using a radiation source doesn't mean you can't create mutations you didn't want to create at will. And because it's hard to create what you want doesn't mean we deregulate cobalt sources for farmers to put in their fields. Right? This is the ridiculousness of the argument with the gene technologies that are of a nucleic acid basis, a genome editing basis, versus a radiation basis. It's equally if hard to create something you want with either one. That doesn't mean you deregulate both. So how hard is it to play? It's getting very easy. During the pandemic period, during the lockdown periods, you could buy genome editing kits over the internet. There's companies that are dedicated to sending them out to do work on yeast. You even had stories about companies, and you can go. I've in the last week or so, I checked the website. You can still go to a website in the U.S. and buy a gene editing kit for tree frogs. So you can do animals, you can do fungi like yeast, you can do bacteria. People were even talking about injecting themselves with these genome editors. And regardless of whether you get what you want, you get an effect, you get an impact. And if it's done at a high enough scale, it becomes problematic. There's two issues here. Not only can you buy the materials over the internet, but if you put in a restriction, so the gene technology bill puts in a restriction about getting some of these, what they're called reagents, the necessary ingredients for causing the genome editing reaction, is to put restrictions on companies that provide some of these reagents to ensure that people aren't trying to make something bad. But already in the US, there have been FBI funded trials to see how easy it is to get around these restrictions with these companies. And it's very easy,
Okay.
very easy to hack those companies. And in part because you don't have to be intending to work with a known dangerous organism to create something inadvertently dangerous. So that's also a failed strategy. So not only can you get these tools fairly freely over the internet, they don't require a great deal of sophistication to use. You can train yourself on YouTube videos to use genome editors effectively. You don't need to have a PhD in molecular biology to use them. You just may not get what you intended to get. And the problem for that I see for New Zealand is that in adopting what would become absolutely the most permissive environment for free use of genetic engineering of a type using genome editing, we would become the world's most liberalized, deregulated environment. The problem for us is that if you are a company or a scientist homed in any other country that would restrict your use, you'll come here.
Mm.
Why not? Let's see if you can create what you want. And if you can't, you don't care. But most importantly, and I think we can't, we for farmers, you've got to keep this in mind. Genome editors are not just tools to produce something that you're going to release into the environment and can be used for the benefit of the person who releases it, say the farmer. These technologies are powerful mutagens, just like radiation sources and some chemicals are powerful mutagens. But the mutagen is itself not a hazardous substance. So it doesn't have to be regulated or controlled in the same way. But you can use it to kill. In the same way you could use a hazardous substance that's a mutagen to kill. And if I were so inclined, and I'm not, by the way, I just want to make sure everybody realizes, uh, if I were inclined to want to harm New Zealand industries, genome editing tools that are going to be deregulated would help me to do so. So I could start to undermine fundamental ecosystem services just by releasing a certain mutagenic activity that would hurt those organisms. I don't have to have the intent to create a modified product for sale. I may simply have the intent to undermine an existing ecosystem service that would reduce the fundamental efficiency of New Zealand agriculture in key markets and key products that are important for our markets, and then become more competitive as an industry located somewhere else.
Well, that is absolutely terrifying, but it's really cool to have that conversation, and it really highlights that unintended consequences of, I guess, the current bill, but also using these tools. One question that I've always wanted some clarification on is, say, if you have a non-GMO species and a gene-edited species, how easy is that to cross over, whether it be livestock or a crop or a grass?
All right, so there's different ways in which we get this
Okay.
flow, right? If you, and I've already
Yeah.
discussed one. One is not that you cross a yeast with a cow,
Mm.
right? So if I have a genome edited yeast and a non-GMO cow, I can still get the effect of a cross by contaminating whatever product the cow makes with that GMO yeast. Okay. And if I can't control that microorganism, I can't segregate that microorganism away from my other organism like a cow, even though they're so hugely different in
Mm.
size. Okay. But the way you're talking about is what we've had as a problem ever since the commercialization and release of certain transgenic organisms. And that's that ability of them to
Mm.
breed and bring together or mix together transgenes with organisms that don't have a history of being genetically modified. Now, agriculture does have segregation tools. The larger the scale at which you have two different agronomic or livestock systems in operation, the larger those scales of each to one another, the more likelihood of contamination. You just can't avoid it. So in the US, obviously, the staple crops like maize and cotton, those kinds of crops, they've become almost exclusively GMO. This is argued to be because farmers see the advantage and the cost benefits of using them. But it's also because if you're a non GMO farmer, it's just prohibitively expensive to prove that you're not contaminated, right? So there's a momentum to that machine. And that the outcome is larger and larger monocultures of the same kind of cropping philosophy, which is GMO. That's the ratchet effect of adopting it. New Zealand has a far more, even though we have some kinds of big monocultures like dairy and some cropping monocultures in things like the Waikato and Canterbury areas. Even though we have that, they're tiny in scale to the Americas. Argentina, Brazil, the US, Canada. I mean, tens of New Zealands fit into their monocultures. So our biggest monocultures are a local farm almost in those countries. So the intensification and co-technology model that has driven those types of GMO developments just don't pay off here. We can't get the kind of conversion efficiency from using airplanes to spray Roundup for 7 or 8 hours a day flying in one direction. So we have too much diversity in our agro-ecosystem here to benefit from those kinds of traits. And it also means that it's really expensive to come up with the same kinds of segregation solutions to allow different farmers to coexist because the scale of production is too small to pay for that kind of segregation that works in those large countries. Now, so that doesn't mean it's impossible, but it's probably impracticable for most types of cropping systems we have. I think with animals, it's going to be easier to manage. With plants, it's going to be more difficult. With microorganisms, no way. All right. Other than using containment for fermentation, no way. I guess the answer is it's possible for segregation, but even to make that possible, you have to know what you're segregating. One of the most famous examples of how unintended effects arise when you with genome editing is the genome edited polled cattle in the US. So the company Recombinetics had mutated using a genome editor, one that's even less likely to cause off-target effects than CRISPR-Cas. It used that genome editor to knock out the gene called polled that's responsible for horn development in a line of cattle that naturally still produces horns. And this was, billed as an animal welfare issue because if you put the cattle together in too high a concentration, they gorge one another, and that hurts. It causes higher levels of infection, uses more antibiotics, et cetera, et cetera. All of it sounds like a good news story. Recombinetics was a fanatical advocate of using this kind of approach to solving problems like overstocking, the concentration of cows with horns. And when it produced these cattle using a genome editor, which was intended to only produce a mutation, not insert a transgene, and done under conditions which are even less likely in CRISPR-Cas9 to create a transgenic organism, when it did this, it put out press releases and made statements about how they have checked these cattle genomes. There is absolutely zero chance of a change that they didn't anticipate and a change outside of what they intended to make. Those cattle genomes were sent to, so the files from the genome sequencing were sent to the US FDA, not because the US FDA required it, but because contemporaneously the US FDA was considering its own regulations on the use of these techniques in animals. And it asked for the information simply to train its own internal processes to evaluate its regulations. And the US FDA staff found that the cattle genome didn't have only the changes that were intended to be made. that there was an insertion of 4,000 nucleotides from bacteria, including full antibiotic resistance genes inserted into the cattle genome. This isn't, oh, was there a change at a single nucleotide that could have occurred in nature spontaneously? No. Despite this really bold, red flag to a bull approach by the company to say that they have proof that you can use genome editing to not create something that you didn't want to create, they didn't look. They simply didn't look. 4,000 nucleotides is not easy to miss.
No.
And what the FDA found was that they didn't look for genes from the most obvious source, which were genes from the reagents that they used for the genome editing reactions themselves. So it's possible that if we deregulate some of these techniques for use on animals, that's where we will get unintentional genetically modified animals, which then we amplify through breeding, not because we were intending to segregate them and failed, but because we didn't know that we even made them.
Yeah, I think that really highlights a lot of concern from those within the industry that want to either stay non-GMO within their own farm system and use that as a way to gain access to maybe a premium market, or those in the organic industry as well who are very concerned about this. So
Yeah.
it's, by the sounds of it, it is going to fall on them to prove that they are non-GMO and within their system. And as you say, overseas that's very expensive. And for me, that feels a bit unfair that they have to go and prove that it's not within their system because everyone else is deciding that it's a free-for-all, or we've got loose rules now and most people can essentially trial different products out in the environment now.
And what I would add to that is segregation is expensive, and overseas have shown us that it's expensive, but the reason they can afford it is because of the size of their monocultures. So they have so many silos, so many, seed collection places that are in the middle of tens of thousands, hundreds of thousands, millions of hectares of the same crop, that segregation then becomes at least affordable. And we do not have that type of agricultural system here. So it's not just that it's expensive, it is only possible if you have the scale of the Americas and maybe a few other places in the world to have those kinds of monocultures.
Yeah, I think that really highlights another point for me is I guess they always highlight that it'll be reduced costs or inputs going into these systems that are using it, whether it be a crop or a ryegrass or say the livestock. But you're saying that only really is achievable at a certain scale, which New Zealand doesn't have currently.
I wouldn't say always, my imagination isn't that big, but whether this is a pathway to routinely delivering those kinds of benefits and routinely avoiding the bad inputs, that's what I can't see, because we've had these tools for 50 years and we haven't invented any way to achieve what you just said, right? And we've had them in countries that have been very permissive to their use. So it's not suddenly going to change just because we deregulate something here, that all of a sudden we're going to have this onslaught of plants and animals and microorganisms that have all of these low input magical properties, because we could have had them for the last 50 years. It would have been harder and slower to make, but not impossible to make. So what I really think is we'll be trading a reliable, proven system for boutique novelty items, biological novelty items, and of small market. The market is so small, it doesn't perhaps justify the costs of navigating a regulatory environment such as we have. But if it can't meet those reasonable regulatory costs, how really important is that market?
Oh, 100%. And I think you're really highlighting something for me that is really important about this conversation, is that we trade on a certain image as a country, and from a marketing point of view, not being non-GMO is actually increasing our status of being able to access those niche markets that are willing to pay more, and because that is a growing market within the world. Well, how do you think what we're currently proposing will either enhance that imagery, or do you think it's a risk to our marketing?
All right, I'm not an economist or a
Yeah.
marketer, so I don't know about these things necessarily. But it's often said that we do get a
Mm.
premium from this, whereas it's not my area to prove or disprove this premium. What is clear is that already we have had massive costs whenever we get inadvertently contaminated with something GMO, beginning with Corngate, and then all of the events in the early part of the century with the maize seed that was imported from the U.S. and grown here that had transgenes. We know how expensive it is if our trade gets disrupted because of the detection, real or otherwise, of a potential GMO. So whether or not we get a premium, I don't know. But what we do lose, definitely, is our profit if we have a GMO material that we didn't want to have, didn't think we had. So there's definitely a cost to contamination, and the easiest way to contain that cost is if there's no chance or very limited chance of getting contaminated because your entire agricultural system is not using those kinds of materials as inputs themselves, right? Then nobody has a unique risk that comes from being contaminated, and you have very easy gatekeepers to keep that input out of the country to begin with. So when the seed comes on the boat to test a final test, or when the animal germplasm is transported here as a final test, it's easier to control it at that stage than it is after it's amplified in the environment and you get trace amounts in your product lines that then lead to trade disruptions.
Absolutely, and I guess it's the blessing of New Zealand being an island down in the South Pacific, completely surrounded by water, is that we do have some good borders. So,
Except
except
for
for fish,
fish.
yeah. So, if our current regulatory framework, do you think it's doing the job? Because we are still able to do these things in the lab, and like you say, if we're able to meet a certain level, they would be out in the environment now, and we would be able to use them. So, do you think our current framework works, or does that still need tweaks as well?
What I would say is there's no evidence in my mind at all that I have seen, no reliable, verifiable evidence that our regulatory system has kept useful GMOs out of this country. What I see is scientists complaining that cost of regulation is preventing them from inventing magical organisms. But been no serious research done by people other than plant biotechnologists complaining, surveying our biotechnologists, no serious research to show us that regulations have stepped between us and a genetic utopia. None that I'm aware of. So what we have is just this axiomatic regulations cost too much, and that is holding us back, and no real evidence. Therefore, I think our current legislation has the benefit of the doubt. It has been successful in many ways at avoiding problems here that other countries have had to deal with. There's no real evidence that it's had an economic impact on us. It is enabling legislation. It aligns us with our international obligations under the Convention on Biological Diversity that says you can release GMOs into the environment. You just have to do a case by case risk assessment and do anything else to get social license that your country requires you to do. So there's nothing that prevents us from having these organisms if they really were of market value or conservation value. It does allow it. It is more difficult under our current legislation than it is under the proposed legislation. And in part, that's because we simply stop looking for risk and harm in a large proportion of the genetically modified organisms that we could make using the new legislation. The new legislation also makes it easier for some organisms that are still to be regulated to be released. And that might be salvageable for a tweak in our current regulatory framework, provided that really issues of risk and not just comparative hazard are the basis for expediting the release of those organisms into the environment. And that's a whole nother big conversation. But essentially, it means that you can't just say, because this mutation looks like another mutation, it's automatically safe. You have to really look at risk. But I think it is possible to tweak our current regulation to expedite the release of genetically modified organisms, should there be a reason to do so. And that is a saner way to do it than to throw it all out and write a bill that has such creates such massive vulnerabilities onto so many sectors in New Zealand. I think there would be a middle ground there. But we see an almost fanatical drive to become this, unusually, extremely deregulated place.
Yeah, and I guess we're seeing fanatics on both sides of the story, really. So I think
Yeah.
we've got to recognise that. But if I was to say create a crystal ball and you could create a new framework, how is there anything that you would change from what we're currently doing, or are you looking at that a bit of a hybrid from what as you were just discussing then?
Well, I think the kinds of things that I would change are ones that are super
Hmm.
easy and address a large source of the complaints that come from my colleagues. We invented the idea of containment to control the risk of gene technology. We invented that way back in the 70s. Now, it wasn't that amazing of an invention. We always used laboratories, and we always used them in such a way as to keep things out as well as to keep things in, because the types of experiments you were doing in a laboratory could only happen in a laboratory by controlling those environmental variables. So a laboratory was needed to improve the efficiency of anything we did to the point where we could see it to test something. In the 70s, the idea was, well, since laboratories already do this, and since most of the harm that can come from making something you didn't want to make would arise if it got out of the laboratory, let's just use containment as a way to mitigate the risk of using gene technologies. And then you release something from containment only after you've proven that it has an acceptable, anticipatable risk. And that makes sense to me. It's not perfect, but it makes some sense. And because containment will work for all species and all kinds of techniques, you could probably relax the regulations around the use of the techniques within proper certified containment facilities. Reduce that kind of regulatory administrative burden for the daily use of gene technologies in containment, and possibly increase the number and pace at which you get organisms that are of potential value without necessarily having to open up the whole environment to everything that somebody might make all at once. So I think you could tinker around the regulations for use in containment to make them much more umbrella like. And you could probably do a bit of tiering in the risk assessment for the release of organisms that you intend to release once they're characterized. And that would go a long way to addressing many of the complaints I hear from my colleagues. And without, though, throwing the baby away with the bathwater and the fundamental case by case risk assessment, which we depend upon to provide us with the tools to ensure our products are not admixed with unintended genetically modified material and doesn't go freely into the environment and amplify itself.
That sounds relatively practical to me, although I don't understand it all as well as yourself. So, if for the farmers who are from New Zealand currently listening to this, what would be your message for them around this conversation that we're currently having in New Zealand?
My message to them is first to be clear eyed, hard nosed about the promises that are being made. The same kinds of promises are 50 years old. Every time there's a new tool invented in the gene technology suite, you get the same kind of claims. It's more precise, it's safer, it's faster. It'll deliver what you always wanted but could never have dreamed of having available to you. There's 50 years of history of this, and what we have are herbicide resistant crops and insecticide producing crops predominantly. That's the main product released into the environment. There are other products of gene technology, primarily in the fermentation and medical areas, but they don't necessarily require the release of an organism into the environment, so that doesn't usually impact on a farmer. The kinds of things that are being promised to farmers, those kinds of things have had the same promises behind them for 50 years and have never been delivered. That doesn't mean that it's impossible for gene technology to one day deliver such a product, but it can do so safely developing that product in containment, proving that it can deliver that benefit without unknown changes that could lead to harm before it's released into the environment. So, as a farmer, my main concern would be, what do I have to lose rather than what are the promises of gain?
I think that's a great message there. So, Jack, I finish up my podcast with a couple of quick questions, but I'm going to put one to you here, and that is, what is a force of nature to you?
Yes, a force of nature. And that, I mean, nature is amazing and powerful, and we know good and bad things can emerge in nature. We know we can get a pandemic, and we know we can get a huge diversity of species without human intervention, just from nature. So, nature has massive forces, if you want to put it into those terms. But those forces do not mimic a technology. And that is my key message. When you look at what can occur on Earth, from dangerous dinosaurs to spontaneous fission reactions in the bowels of Africa that went for hundreds of millions of years prior to the evolution of human beings, all of those things can happen in nature, just like humans can make some of those things happen using the tools of their technology. But you can't dismiss what we can do with our technology just because over the 4 billion or so history of the Earth, something similar occurred once somewhere. We have the ability to change when a harmful thing is made, how many of those harmful things are made, and where those harmful things will be, and that is risk. That they can be harmful, that's a hazard. So nature produces hazards all the time. It very infrequently produces a new risk. It very infrequently puts something that occurs once somewhere on the globe in exactly the right place to cause harm. We notice what it does, but it's infrequent compared to how often it creates something hazardous. With technology, we can't control the risk. And that's why we should regulate technology. It's the one imperfect tool we have to try to control the scaling effects of harm.
It's a fantastic message to finish on. So for Jack, those who want to follow your work or connect with you, what's the best way to stay in touch?
Well, the University of Canterbury website has all my details. It also has a repository of things we've published, lists of our publications, and contact details. So what I would say first, and it's easy to do, is to look up the University of Canterbury website.
Awesome. All right, I'll put the link to that down below in the podcast. But thank you very much for your time and your incredible knowledge on this very complex topic. I really appreciate it today.
Thank you, Conan. It's a pleasure to speak with you.